Hey, how are you guys? How are you guys doing? Anyone started the lab yet? Just wait a few seconds here for people to access the Zoom link. So how is everyone doing? Like, how was the first week of the lab, if someone attended? Anyone? Do you guys hear me or not? Oh, okay. That's good. Okay. Any challenges, any major issues? Good practice, okay. Okay, looks like number are decreasing because of what? I don't know. Is it because of the recording of the lecture? I don't know how. Do you guys really look at the recorded lecture? Okay. 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 Yeah, because if you are attending now and you are seeing the lecture, that means there are some other people are not either seeing the lecture or even attending. So it doesn't add up. I don't see that many people, like 30, 40 people views the lecture, the recording. So anyway, we'll keep doing this. We'll keep doing the recording. There's no problem. The most important thing I would like to keep, reminding you that try to use the time to ask questions, try to use the time to understand and have more discussion on like one-on-one, like trying to really get the best, out of the course. Okay, let me share the screen and then we'll start our lecture today. We started last time at one of the examples. Let me just open this. I hope you can see the screen here. Let me open the chat so I can see everything. So can you see the screen? Slide, I mean. Okay, thank you. So so last time we talked about some of the principles for fluid statics, and if you remember, we talk about the pressure as a scalar quantity. We look at the pressure at any point, and we find out the pressure in every direction at any point inside the fluids is equal in all directions. So which means that basically pressure does not depend on the direction of the fluids. Forces are. So the pressure forces will be basically perpendicular to the surface that you are looking at, but the pressure itself does not depend on the direction. And then we move to the second principle, which is basically for a static fluid. And you remember, this chapter is dealing with a static fluid. So the fluid is stagnant, the fluid is not moving, the fluid has no shear forces acting on it, which means that I can apply those principles. So in a horizontal plane, so we're looking at at any point in the fluids in a horizontal plane, the pressure will be the same, and we prove this, right? And then we move to this, the third note in this chapter is talking about the variation of the pressure inside the fluid. So in this case, if we are looking, for example, going in a deeper position in the fluids, we found that the relation between the pressure at the lower point or at the lower depths will basically will be higher than the one at the top, with an increase of a certain value related to the head of this pressure. Okay. And then we move to the last in the last part of the lecture to look at what we call it, like, you know, the hydraulic transmission, and we explain you know, how can we use what we learned so far in application when we are trying to lift like a heavy, you know, heavy load using a smaller forces by doing what we call it the hydraulic jack. Right. So last time we kind of, you know, discussed this problem, but we didn't have the time to go over the solution. So remind you by this, like we have a jack here, like, you know, hydraulic jack, and then we have a piston. The smaller piston here has a 1-inch diameter. The bigger piston here has a 3-inch diameter, and we have the load of 2,000 pound force. And we mentioned that the fluid is inside here is oil, and we have a handle here that is basically pushing, you know, trying to push, like, you know, this piston down in order to lift these loads. Okay, the specific weight of the oil is given in the problem. Okay, so just before we started this, one of the assumptions that we have to keep in mind in this case is the fluid is static, right? Because I got a question at the end of the last lecture talking about, like, you know, how about if the small piston moves a little bit down, and then, you know, what will happen to these points? Remember, we are not talking about any motion here. So this handle is actually in this position given in this problem, as per the schematic, it is located at the same place. So we are not considering any motion here. I agree with you that in practical, the idea is to lift the load. It's not just to hold the load, right? Many applications. So, you know, we'll have motion. You will have even motor that is doing multiple strokes, and you know, try to find out what will be how many strokes, for example, to lift this weight a certain distance. That's not our concern in this problem. This problem is basically asking you to find out what will be the required force F in order to, you know, basically hold this load or like lift this load, right, at this position. Okay, so the first assumption, this fluid is static. And of course, you know, one of the assumptions that we all know from chapter 1, that the oil here is, the fluid in this case will be incompressible. Okay, so in this case we have, you know, this piston is not going to go down. This piston is basically, like, you know, will stand in place. Okay. So how can we start this problem? Can you tell me how we can start this problem? So for a static, you know, problem like this, the summation of forces equals 0, sure, but okay, where is the summation of force? Everywhere, right? Every point inside the system, the summation of forces equals 0. How can we use these in order to solve the problem then? Can you tell me, for example, at a certain point, I'm not sure, I've seen somebody is putting his camera on. I hope you mean it, or we can see you. I don't know if you can, Arsenally, yeah, your camera is on. Okay, just make sure that, you know, you don't mind. Anyway, okay, so forces is equal 0 at everywhere, which is fine. Yeah, submission of forces in any direction equals 0 for a static, fine. But how can we use this? We have a load here. This is W. Okay, and we have the force here. We have a lots of reactions here, right? So if you can consider this, you remember mechanics, right? Right, forces here, right? So summation of forces at any point is equal 0. It's not going to help us, right? Because once you start looking at every single point, you will start looking at other reactions and so on. But let's start to point by point. Let's talk about the, you know, what's happening here when this is kind of, you know, moving in this direction. So basically what you are doing here, you are kind of putting some force here, right, F. And if you consider, for example, this is 0.1, okay, let's use another different color. So this hinge here is 0.1. I can use these to say that, okay, this is a hinge here, this is a force here. If I break this element here, so the force acting here will be the same force acting here, right? So this F1 here, and this is F2 here, right? Okay, so I can say F here in both directions are equal, right? Okay, what else? I've seen here some people talking about the moment, right? I think this is the right, the right approach to take. What kind of moment? Where is the point we would like to apply the moment? Can I say that this is, this is 0.2 here, right? The hinge here, right? And now if I say that the summation of the moment around 0.2 is equal 0 for the static, right? So exactly, right? So in this case, I can say that, for example, here, if I put this handle here, separate, I have this point here, this is 0.2. Now I have F here, and I have F here, right? I know the distance here. I know the distance there, right? So this is what the total distance is 16 inches. This distance is 1 inch. So if I can say that, for example, the summation of moment is around 2 is equal 0, I can say that basically F, right, times 16 will be equal to the small f here, right, times 1 inch, right? As long as the units in both sides are the same, I'm fine with that. So F here will be, basically like, will be equal to F over 16. Okay, and I can just say that this is the first equation. So what other point of analysis I can make here? Let's look at the fluid now. Okay. So let's look at the fluid here. The pressure inside the fluid in the horizontal plane is equal, right? Once the fluid is connected, the same fluid. So I can say, for example, like, can expand this here, and I can say this point A here, and this point B here, right? Same fluid, and the same horizontal plane, right? They are equal, right? So in this case, I can say BA is equal BB, right? Now for point A, I can relate the pressure at point A in terms of the force, right? And force and area, right? So at point A, it looks like the small piston that has an area that is small area, that is 1 inch diameter, and the same force here, right? From the side that is reacting over the handle, it is the same force that is acting on the piston if you break the element at this location. This is from the mechanics. Everything is static here, right? So I can say, for example, here, this F here over the small area is equal to point B, which is anyone? W, right? So it's W, which is a big weight here, right? So this is a weight W that we are talking about here, right? Over the area, the big area of this piston, or the area of the piston that is big, right? I can take from this equation, like, F here will be basically, it's A over A times W. And I can say that the area here is pi over 4. This is a 1 inch square, pi over 4. This is a 3 inch square. Remember, you know, dimension is okay because all are inches. We are dividing both together, so there's no problem. There's no point of converting and then coming back in, right? And divide both units at the same time. So W here, the most important thing here, you have to remember, if you put W here in the bound force, which is the 2000, that means your F small will be the same unit here. So F small here will be, you know, let me just see here when I calculated. It is about 2.2 bound force. Okay. So this is basically your second thing, right? So if you go back to the first equation here, I can get F here as it's F over 16. So which is basically 13.88 bound force, right? It looks like, you know, you can see here from this problem that you kind of reduced the force. First, you reduce it by going from this big piston to the small piston. You have 2000 bound force. You only needed at this piston about 222. But having also this kind of, you know, cantilever, like, you know, this element here where you have the handle, you are even reducing this with a smaller value. And then you end up with you only need 13 bound force in order to lift this heavy weight. Okay. Any questions in this? Okay. As I mentioned to you, like we're trying to, this is a very, like, you know, simple analysis for simple application in fluid mechanics. And that's the idea of this course, is trying to make you relate to like what is actual application in terms of like the material that we are covering. So hydraulic transmission, this is the first, you know, piece of information you have to understand when you are talking about hydraulic transmission. So most of the application later on will be much more complex, but it's still dependent on transmitting forces based on one point that has same pressure of the fluid, the other point has the same pressure. You play with the area. You are kind of scaling down the forces required in order to do this. If the force is required to be acting linearly, like as we said, as we've seen here in the handle, or this force needed by applying some kind of a motor added, like, you know, a power at some point in order to lift like higher load on the other side. And you can see this in cranes, and you see, you know, it's the same thing, right? Yeah, so it's just playing with the hydrostatic transmission forces, right? Same thing when you are actually applying brakes in your car, right? You know, like nowadays we have a lot of electronics. So, but again, these electronics at the end is doing what? Is doing mechanical motion, right? Is doing, like, you know, a clamping, you know, actions that is holding this disc that is rotating, right? So at the end, even though electronic transmission between when you push your, like, you know, the braking handle to a point where there is an oil, you know, that's why when you go to, like, you know, for the service, you change the brake oil, right? There's some hydraulic lines that is, you know, basically having some oil there. And the same idea, you apply very small little forces at one point of this system, and you are magnifying these forces at another point in the system in order to basically achieve the much higher forces needed. Okay. Any questions on this? Go back a slide. Okay. Yeah, I'm trying to move faster. This will be available to you guys. I'm going to give you all this information and post it. If the ratio between the two diameter is small, the force required, yeah, for sure, right? That's right. It's all depend on, like, the design that you are doing, right? So sometime actually when you are designing, you come up with what area or what piston needed. Like, so if I can, for example, say the maximum human force that is needed that much, and now the load is that much, right? I have to come up with a design. So I have to really design the area for these pistons or for this system in order to achieve this reduction in the power or reduction in the forces. Yeah, that's 56 pound per, yeah. Did we needed this? Okay. Did we need this? Okay. Let me actually, you know what? It's a nice question. And let me just change this problem. Let's say, for example, if this problem like this, let's say, I'm sorry, it's a good question. So this piston area is like that. This is a piston. This is W. This is F. Okay. And this is the oil here. And I know this distance here. I know this H. And I know this oil here. Specific weight is, let's say, 0.56. What do you think is going to happen? What is going to change in this problem here? Can I say, for example, in this case, can I say this point A and this point B has the same pressure? No. So how can I relate point A and point B in terms of pressure? Huh? What can I say about point A pressure? Exactly, it is higher. So point A is point B plus gamma H. Okay, you see the only difference here, if you know, if there are some difference between the two positions, I have to consider, like, please, like, the people are putting the microphone on, make sure that you are muting this. So I have a difference in the height. That means the specific weight of the oil will play a role in determining what will be the value for the second point pressure, right? I don't have to complete this, but this is going to be the difference here. It's just going to be like, you know, another piece of information that you have to add in your equation, and then you fix your other given parameters. Okay, let's get into another, the topic of today's lecture is talking about the pressure measurement. Okay, you guys have heard a lot about, you know, YouTube manometers in your physics courses in the high school, right? And you know, biosometer tubes and stuff like that. You might have seen these kind of, you know, equipment or measuring devices at some point in your science project or science courses. So YouTube is a simple, device using the mechanical motion of the fluid itself to indicate the pressure. Okay, so let's assume we have a tube like this. So this is a cross section. Okay, this is a cross section. Imagine this is a fluid moving inside this, and what you did is basically you drill a hole in this tube and you connect this tube into something like this, like a U-shaped tube. Okay, and there is a fluid here, and we call it fluid 1. Okay, and now we are using in this tube fluid 2. Okay, and let's say that the other end of the tube is open here to atmosphere. Okay, so in this case, what's going to happen? Let's say, for example, if the pressure at this point here, let's say, is equal to atmosphere, what do you think about these fluids level inside this tube? Okay, let me rephrase the question. Let me just say that I have a YouTube like this. okay? And I put some fluid in this tube. And this fluid is like this. First of all, do you expect the fluid height in this U-tube to be the same if this tube is open to same pressure from both sides? Yeah, all right, makes sense. So pressure is applying in this side, pressure is applying on the other side, the fluid is inside this tube. So there's a balance of the forces here, the pressure forces from both sides, okay? What will happen if the pressure at one side is different from the other? It was just like, you know, the fluid inside this tube will basically pushed in the, you know, in the direction of the higher pressure, right? So that's why, for example, in this case here, when you are looking at this this example, the pressure of the fluid inside the tube at point A is higher, and that's why is pushing the fluids to go in this direction, right? So we have to agree that, you know, basically the pressure at point A is greater than the atmospheric, right? Now, let me ask you the second question. Can we have a fluid tube, like let's say, for example, can I have you know, water inside this tube? Let's say water here. Let's say example. Can I have the density of the second fluid is oil? Can I have oil inside this U-tube if I have water inside this pipe? Sure. Yeah. No. Yes. How? Did you try to put oil in a cup of water and the oil can go down? No, you can't, right? So what will happen? You cannot have an oil that is under the water, right? You see here, this is water, right? So what will happen? The oil will escape, goes inside the water tube, right? So you cannot really have this. And that's why, you know, the condition for a U-tube that it has to have a, you know, a heavier fluid. That's why you are using, for example, mercury, right? So in this case, when we are using a U-tube manometer, we have to make sure that the fluid in the U-tube or the fluid at the bottom, right, has to be heavier than the fluid at the top, right? So at any surface, at any contact surface like this one here, you cannot have a water at the top and then oil at the bottom, right? Because basically, you know, the density difference, and this is something that we're going to discuss at the end of this chapter, is gravity force and the buoyancy force, right? So so U-tube is a device that measures you know, pressure difference between 2 points or the pressure at one point, as we can see here, if the other opening is, or the other, you know, leg of the U-tube is open to the atmosphere, right? So this is one of the very, very like common measuring device. Of course, these kind of, you know, measurements, you will put like a scale, for example, here, and you see how much, you know, from how much like a difference between this point and this point, and you can really relate this scale or relate, like, you know, the head of the fluid into the pressure, right? So the measuring element here is the fluid itself, right? So the fluid goes up, or this head, this goes up. We know the pressure is gamma H or rho GH, right? So I can find out the pressure. How about if this pressure varying quickly? Like, you know, imagine like the pressure changing every 0.001 seconds. Do you think this U-tube manometer will be, you know, an appropriate device to measure the pressure? Yeah, you don't think so? And of course not, right? Why is that? Because the inertia of the liquid, you know, the liquid would like to go up and down in this very short period, but because the inertia of the mass of the liquid is, right? And that's why once you get into a much more dynamic forces or dynamic pressure variations, you have to come up with a different kind of devices that is doing this, right? So keep this in mind. I mentioned the YouTube manometer can measure either like, you know, the pressure at a point, if the other opening is open to the atmosphere, or the pressure between 2 points. Let me ask you here, at point A and this point B. What is the pressure at point A versus the pressure at point B? Let's have a fluid flow here. A is greater than B. BA is greater than B. Some people saying same. Okay. Please don't be shy. Like, just, you know, whatever mistake you are doing here, we're just learning, right? So whatever mistakes you are doing here, you are not the first one. There's hundreds of people before you did the same exact mistake. Okay. 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 Are they both open to atmosphere? No. Right. This is a tube, let's say, long tube. Okay. And I'm just, you know, looking at 2 points inside this tube. So why people saying BA is greater than BB? Why you come up with this? Why you think BA? Okay, fluid flow. Remember these, okay? Remember these, because in chapter 4, we're going to come back and say, is only the pressure is driving the flow or something else? Okay, you drop you drop some water at the top of the mountain. It goes down or goes up? Down, right? Is it because of the, you know, the pressure at the mountain is higher than the pressure down? It's a gravity, right? You see here. So we'll get into this discussion when we come back to the fluid flow chapter. But it's a good thinking, right? You think that because this is a tube, horizontal, and it's constant diameter, nothing will move the fluid except the pressure. And I agree with you, right? And the pressure at point A and point B cannot be the same. Why? Because this is not a static fluid. If it's only static fluid, the pressure is the same. But if the fluid is moving, there's going to be some kind of, you know, energy driving this flow. And because maybe we didn't get into that yet, but because of, like, you know, so there's no gravity difference, there is no acceleration difference, there is, right? It's going to be only the pressure. But that's good. And other people, maybe they look at the, you know, this manometer, right? The people see that BA is greater than B. They will look at this manometer, right? You see the manometer is actually pushed in this direction, right? Pushed in this direction, which means that the pressure from this side is higher than the pressure from this side. You agree with me, everybody? Everyone understand this? That's very important, very important. So simple principle, but this is a core of the, you know, the fluid mechanics. Okay, so so the YouTube manometer will measure the pressure between 2 points. First of all, the fluid density inside this YouTube manometer has to be greater than the specific gravity of this fluid flowing here. So it has to be heavier fluid, right? And of course, the pressure will direct the YouTube, you know, elevation in order to show which one is higher and how much is higher from one point to another point. So I mentioned to you, like, you know, if you have variable pressure, you might end up with, like, you know, YouTube and these kind of devices is not appropriate for measuring this pressure. How about if I need, like, you know, to measure very, very high pressure difference, let's say 20 bars and stuff like that. If I get a YouTube manometer or, like, you know, this tube, I need a very long, you know, tube in order to measure this, because the pressure value is gamma H, right? So in order to measure very high pressure, so it's going to be, like, you know, you need a long one. So it's sometime, and actually many applications, you cannot afford this, right? You only use a YouTube manometer when you want to indicate, like, when you I want to see, like, you know, by eyes what is happening there. But it's going to be a very limited application, right? The other application, like, you know, the other type of devices that is measuring pressure is something called Bourdon tube gauge, or the pressure gauge, right? So, you know, you will see this pressure gauge many applications. Everywhere you go in any industry, you will see these dials that is measuring the pressure here. And you see here, for example, here, the unit for this case is bar, right? The bar here is known as the 100,000 kilopascal. sorry, the 100,000 Pascal, right? Or 100 kilopascal. So it's just a scale of the pressure as we explained last time. But the idea of this Bourdon tube is the deflection of the tube as the pressure increase inside this tube. Simple, right? So I have a tube like this. Let me just add this. I have a tube like this. And if you take the cross section here, you will see this is something like that. So the tube here is not like it's not a circle. The cross section is not a circle. It is design, you know, it has a long story if people want to read more about the design itself. But it's a simple, you know, it's a simple theory. When you have a fluid here, of course, this tube is closed from the other end, right? So the tube here is closed from this end, okay? So what's happening if this fluid pressure increase, this tube will basically deflect, right? So it will be something like this. So it will move according to the pressure. It will move like this or like this, depend on the pressure inside. Okay, there's even some toys, like when you are actually pushing air inside these toys, it kind of, you know, open up, right? So this is similar idea of the Bourdon gauge. How about if you take this motion and connect it to, for example, like, you know, a gear here, right? So, and then you have, you know, a gear, sorry, some kind of mechanism. Once this is moved, okay, this gear is moved. And now if you have a pointer here, I can calibrate this motion or the angular motion of this gear to show, you know, with respect to the deflection, and the pressure here. So if I have a scale here, pressure, I can basically, right? So I can find out the value of these pressures. Very simple kind of idea, right? And it's very, very commonly used in many applications. Remember that, you know, for this kind of application, you will see a lots of these dials available, depending on the pressure that you are measuring. Sometimes, you know, you just need to change the Bourdon tube, you know, material in order to go from one range to another range. Some of this Bourdon tube material could be copper. Some of them sometimes is stainless steel and stuff like that. So for a very high pressure and so on, right? So you can see wide range of Bourdon gauge, and I can see it here is like a pressure. So many times when you are walking around industrial facility, they call it pressure gauge, right? So it's a gauge where they are measuring the pressure, right? How about same question I asked before? If I have a variation of this, if I have like a pressure that is varying so quickly, like 0.01 second, right? 0.1 second, even a second. Do you think Bourdon tubes will be, you know, good device for this? No. Why? Because again, it depends on you're looking at this. You're looking at the dial. If the dial is keep doing like this, you're gonna fluctuate and you don't see what's happening, right? So you need to find out something, you know, more sensitive. And of course, again, it is related to the inertia. Again, it is inertia. Why? Because it's a mechanical motion, right? This all mechanical, and all the mechanical system has much more inertia than electrical system. You agree with me? Because electrons can move very fast, right? So, and that's why we come up with a different way of measuring the pressure inside the system using, you know, either like, you know, something called the pressure transducers, something called like, you know, sometimes we use a piezoelectric material that when you actually push it, it will charge in a different value, and then the charge here is basically the current moving inside the circuit. Okay, or like, you know, a wire, and this wire is, you know, is if you apply a certain tensile of this wire, right? So if you have a diaphragm here, for example, and this diaphragm here is, let's say this is our diaphragm. And if you put like a wire here on this diaphragm, and now we are stretching the whole diaphragm, right? So which means that you are stretching the wire. And once you stretch the wire, if this wire is very sensitive, that means the resistance of this wire will change depending on the tensile stress that you are applying. And that's why, you know, some of these devices, we call it the strain gauges. Okay, so the strain gauges here is using the resistance of a wire to relate the pressure. And how we relate the pressure? By, you know, applying these pressure forces here, that is basically making some deflection of this device that we call it the diaphragm in this case. Okay, other application, as I mentioned, is related to a piezoelectric material. And this piezoelectric material is a material, once you are applying, you know, once you are applying a certain pressure force in this material, the charge inside this material will be different, and the current in the circuit will be different. Okay, you guys can spend time looking at this. That's, you know, you will see this in many websites that is supplying, you know, manufacturing supplying different kind of pressure. There's hundreds of other, you know, devices for this. What I want you to understand in this part of the lecture is the measuring device is, it has some inertia. You know, if you are using a fluid in order to measure the pressure, now you need a head of these fluids, right? If you have a dynamic pressure, now you have to find out a different system to measure these pressure variations. Okay, let's look at this example here. Okay, I have a tank here, and this tank is containing some air, gasoline, and glycerine. Okay, so, and the pressure gauge at A is 1.5 kilopascal. So this pressure here dA here is 1.5 kilopascal. Okay, and what is required, and the fluid here at 20 degrees C, all the fluid at 20 degrees C. Okay, I just need to determine the elevation Z in meter of the liquid level. Okay, so where is, you see here, there are some distance here, I don't know, right? Or I wanted this elevation from reference point Z. So let's say here this is point A. This is point B. This is point C. Okay, so I need ZB, and I also need the level ZC here. Okay. Okay, so how can we start this? Let me ask you a question. What is the pressure of the air inside here? Let me see if you guys on the 1.5. Anyone else? Everyone knows that the pressure of the air is 1.5 kilopascal? Excellent. Anyone else? Okay. I got some mistakes in, you know, common mistakes in many exams, past exams. People consider the pressure of this air is atmospheric. You remember we discussed this last time. Pressure of the air will be equal to atmosphere if the air is open to the atmosphere. right? If the air inside the tank, the pressure could be any value, and it's given in this problem as 1.5 kilopascal. Okay, how can we start this problem? Okay, how can I start this problem? Let's say, for example, here it's very simple. Let me ask you first. You know, gasoline and glycerine and air. Which one is heavier here? The heaviest one. What is the heaviest one? Glycerine, right? So, and if you go back, you know, to the table. So if you go to table A3, you will find the specific weight of gasoline is 6670 Newton per meter cube. You'll find glycerine is 12360 Newton per meter cube, right? So you will see, you know, okay, and that's why it's you know, it's put like this way, right? So you have the glycerine at the bottom, gasoline, and then the air at the top. So you agree with me that if I find out, of course, these values are given, right? So you see here, this is 1 meter and this is 1.5 meters. This distance here, if I call it, for example, X, if I found X, I can get ZB, right? Agree? Right? So if I can, for example, call this is 0.1 and the same point here, 0.2, and I can say, for example, 0.1 and 0.2 have the same pressure because it is the same fluid, same horizontal plane, right? So I can say, for example, here, B1 is equal to B2, okay? And B1 is equal what? What is B1? B1, 1.5 kilopascal. So 1.5 kilopascal, you just make sure that we are using the same unit. So let's say, for example, you know, it is Pascal. So because we have the Newton per meter cube, SI units, this is kilo. So we just multiply by 10 to the power 3, 1.5, 10 to the power 3 Pascal, which is Newton per meter square. How about B2? This is atmospheric. This is open to atmosphere. What is the atmospheric pressure in this case? What is the atmospheric pressure? 0. Why 0? Because the value for the air given in this problem is gauge, right? Which means, or the reference is atmospheric, which is 0, right? So I have 0 here plus simply is, you know, this distance here. So this distance is filled with gasoline, right? So the distance here is, it's basically gamma of this gasoline times this distance of the gasoline, which is X in this case, right? So it looks like I have this 6670 Newton per meter square, so I can find out X here. So X here is, when I calculate it, it is 0.224 meters. Okay. If I'm interested to find this, you know, the level here, not from this point, but from the whole, like, you know, the reference Z, I can just add this distance here, which is, you know, ZB is equal to this X plus 1.5 plus 1 meter. So it is about 2.724 meters. Okay. What was the 0 again? The 0 is the atmospheric pressure, because we are taking the reference as the pressure, the atmospheric pressure is our reference for this, because the pressure of the air is given in the gauge. That means we are using the atmospheric as a reference. Okay. So let me, sorry, I just added this without. Oops. So I have this. So how about this elevation here? I know this distance also. It is y, right? If I know the distance, I will just add this value here. So basically I can find out z of point C. Okay. I can say, for example, in this case, this is 0.3 and this is 0.4, right? Same horizontal plane, same fluids, right? So B3 is equal to B4. So can you tell me what is 0.3? What formula, Mohammed? What formula did we use? What formula? You didn't even start there, right? Gamma H. Well, this is not, this is, yeah, that's not, I don't call this as an equation that we have to give you, right? In order to solve. This is very like simple, concepts has to be in your mind. Okay, so in this case, what we have for the pressure at 0.3. No, don't be sorry. Don't be sorry. I want you to remove from your head that we have to really find out the formula and apply it into. Okay. So I've been talking about this all the time. Try, please start from the basic principles. There are some people actually like, for this kind of device here, they have an equation at the end that they put the, at the end in the equation, just substitute the values. That's not the idea. If you start from the same principle, from the basic principle, the same way as I'm doing now, so you don't need really to understand so many formulas. In few slides, I will show you there's some equation that will be given for you because you don't have to really memorize this equation and stuff like that. Okay. Don't ever be sorry about any question you ask. Okay. So B3, B4. So how can we, what is B3 in this case? What is B3 in this case? Again, 1.5 plus what? You are here, you are carrying all these loads, right? So which means that in this case will be the B of the A plus, or the gas or the air plus gamma of the gasoline times this H of the gasoline, right? So it's 1.5. Now we are at 0.3, okay? Equal to, what is B4? Plan exactly 0 plus, if this distance y is a distance of a Gill stream, right? So I have distance that is, we call it y in this case, times gamma of the Gill stream. Okay. So of course, this is 1.5 10 to the power 3 plus gamma of the gasoline is 6670 times 1.5 equal to 0 plus y times the glycerine is 12,360. I can get y in from this equation simply by calculating this number. So it's 0.3 meter. And it looks like, Z of point C is a little bit far from Z by Y plus this distance here, right? So it's 1 plus Y, so which is 1.93 meters. Okay, they're very simple type of problems. Okay. There are some other problem. I don't want to I want to get into more other part of the material. So we'll just start this problem and then you can complete it yourself. Okay. One important thing about this problem here is the system is open to atmosphere. So this is atmosphere. Okay. On the right side, L is given as, this L here is 120 centimeter. And remember now, this is an inclined, surface. Does the pressure increase in the depths with a vertical distance or the inclined distance? It's a vertical distance. And you remember, because it's basically because of the weight, and the weight is acting vertically, right? So I don't care about any inclination of any, fluid level. The point here and the point there, it's only changing because of the gravity force, which is acting on the vertical direction. I think some people missed this point here. I'm getting Y, right? And I need ZC. So I need this ZC. So it has to be what? It has to be this distance plus this distance, right? This is 1. So this is 1 meter. So you can just add 1 plus Y to get ZC. Let's go back. Okay. So the first thing is make sure that you understand what we're talking about here. This is 35, right? So this distance here is, what is the distance here? This distance here is, this is cosine, right? So this is sine, this is cosine. So this distance here is L cosine 30. 35. Okay. This vertical distance here. Okay. The other trick in this problem is you have an air, and this air is actually in this side, and you have an air in this side. Okay. And he's asking about this BA. So we need to find out this BA. Okay. And then you can solve the other problem. If BA is given, what will be the length L, right? But the first problem here, if L is 120 centimeter, what will be the pressure of point A? There is an air here, and there is an air here. What do you think the pressure of this point here and this point here? They both have air, right? Agree? You both have air, right? Same, right? Yes. Everybody agree on this? The pressure of this air here equal to the pressure of this air here? I think the other people suspicious because I asked the question again, right? Why no, right? I don't care about the height here. This air is trapped here. It's almost like in a container that is separate from this container here. I don't know, right? It is air here and it is air there, but nothing mentioned about if air in the system will have to have, right? If the air in the same space, like the air in my room here, and the distance is, like, remember we talk about the distance for the air, it's only change if you are flying an airplane, like a very high altitude. But once you are like in the same space, the pressure is the same, right? Let me tell you something, okay? So the pressure, let's say, for example, this is 0.1 here. Okay, let me just here. Well, let's call this is 0.1 here, okay? And okay, so we have an air here, so I have the pressure at this point, and this pressure, let's call this 0.2, or I don't want to call it because, okay, just let me call ABC. This is B, this is C, this is D, right? Okay, so point B and point C are the same pressure? No, right? Point B has the same pressure of this point here, right? Let's say B dash here. Why? Because it is the same fluid, horizontal plane, static, everything, right? So I can say B at point B is equal to B dash, right? And what is the pressure at point B? is it the same as point A or not? This is all air. Yes. Why? Because it's all air, and the elevation of the air doesn't change that much the pressure, because the density of the air is very small. So point A here is basically the point A, right? Equal to this point B dash. Okay, this is the first equation. Okay, how about point C and point B? Which one is higher? B or B dash, right? So B dash is higher because it's basically at the bottom, and then you have a fluid here that is mercury, right? This is gamma mercury, right? So I can say, for example, here, this point B dash is equal to point C plus gamma mercury times H, which is this distance here, which is 32, or like, let's put it in the 0.32 meter minus 0.15. So the distance here is this whole distance minus this distance, right? So this could be your second point, okay? How about point C and point D? D is higher. Somebody saying D is higher. This is air. You still seeing it higher? It's the same, right? So basically, in this case, point D, this is point C. Okay. Yeah. So point D is equal to point C, right? So basically I have this, right? So I have a problem here. So we have, this is 1, 2. I can say this is point 3. How about this point here? I can call it D dash. How about point D with respect to point D dash? Say D dash, right? So remember, you see here, point C, this is point D, right? B dash here from this side is what? This is atmospheric. And it's going to be some distance here, right? So what is this distance here? So BD is equal to BD dash, which is 0 atmosphere, plus, let's say this is our X, right? What is X here? So if this is 35°2, right? It's going to be this distance, you see, right? You see this distance here. So I need this distance. So I can say that, for example, it is this whole distance, right? Minus 18, right? So this whole distance is, remember, it is L. First, it's gamma of, what is this? This is water. So it's gamma water times the distance here, which is L cosine 35° minus the 18 centimeters. Okay, of course you have this. It looks like, you know, it's going to be a straightforward. I know it's step over step over step over step, but this is a way that if you have any complex problem, you can divide it into small little things. Okay. I don't know what do you mean, Adam? This is the shape is given in the problem. We give a vertical. I don't think you should change the layout of the problem in order to solve the problem. Okay, you know, and let me just conclude this, and then I will give you a simple trick that people all the time they are using in order to solve these manometer problems, right? But let's say here, for example, this is your force equation, you are actually, you're taking BC and put it here, right? Because BC is BD, right? So from equation 3, you can put it in equation 4. And now from here, you see this BC here, you can put it in the equation 3. And then you have BA here, which is, right? So you go substitute from equation 1 into 2, and from equation 2 into 3, and then from equation 3 into 4. You will get the number that you want, okay? Some other people, I mean, like, a little bit kind of, they know already fluid mechanics, so right? I don't want you to think the same way because you're still learning your way, right? Some people saying that every time I go down, I increase the pressure by gamma H, unless it's air or gas, okay? If I go horizontal, it is the same, right? But it has to be in the same fluid. So people will say that, for example, like, let me just do this. Oops. It doesn't, okay. Yeah, it doesn't, anyway, let me just, they said that, I started with 1 point, one side. So this is BA, okay? As I go down, okay, I go down like this, but this is air, it's gonna be the same, right? So now I'm here, okay? So every time I go down, I add, every time I go horizontal is almost the same, right? So in this case, B air, all the time is just be air. There's nothing increasing here because it is gas. I move here, no change, right? Now I'm going up. So I go up, I decrease, right? Because you go down, you increase pressure. You go up, you decrease the pressure. If you go up like this, that means it is minus. And now you are basically mercury. That means gamma mercury times this distance here. So, right? So it is 0.32 minus 0.15. I go from here to here, nothing changed. To here, even nothing changed. Why? Because this is all air. You see here? So now I am still there, right? Still the same value. Now I go horizontal, same value, okay? In order to go all the way, that means I have to go like this. So it's gonna be minus again. But minus will be basically what? Minus this distance here. And what is this distance? Is L cosine 35 minus the distance here, which is 0.18. Equal what? I am now here. Equal what? What is the pressure here? 0, right? If you look at this equation and you look at the combination of equation 1, 2, and 3, and 4, you put all, the equation together, you will end up with the same exact equation here. So some people, they just go one step, at the time. You increase as you go down, decrease as you go up. Make sure that when you are going in horizontal, you are in the same fluid, okay? So it's only 10 minutes left for this lecture, and every time I spend so much time than I expected. I want to start a new topic, but I don't want to start it at the end of the lecture. So I will just leave it to next lecture. Any questions? Okay, not sure if it's a question or it's yeah.
I have a question.
Yeah.
So let's say it was mercury and water. This is hard to explain without showing you.
What do you mean mercury or water?
Could I annotate something on the board? If it, I'm able to. Can I just show you a diagram?
Sure.
So this is not a YouTube, but let's just say this is. So up to here is water, and then here is mercury, and then
what is the line in between? What is this line?
Sorry, it's a separation.
No,
Oh,
there is no separation like this. There is nothing like this can happen. You cannot
Oh.
have like a fluid like this.
oh,
You cannot have. You put like a water, you cannot have a liquid standing against the other fluid without one is going up and one is going down.
could you explain that a little more?
If you throw some liquids in a cup, some will go up, some will go down. You are not going to see like half of the cup on this side is different from the,
half
right?
on the other side. Okay. No, what I was trying to say is that.
So we can push this a little bit to after we finish the lecture, and then I can maybe discuss with you.
Okay.
Let me see here. Okay, do we have? We need air in between. I don't know. I'm lost here. There's so many questions here. Okay, we need air in between. I don't know. Where is the questions? Okay, that's fine. So let me just conclude the lecture. Okay, and then once I stop the recording, we can even go and spend time talking. Okay, any questions so far just before closing the recording? Okay, let me stop the recording and then we can spend all the time discussing this. Stop recording.